Hi everyone, my name is Patrick Imo, and I will be discussing about the Border Gateway Protocol, BGP. We'll be taking a deep dive about this to see what it all means. Rundown of agenda will start with the introduction and then BGP basics, go on to see how BGP path selection works. Then we'll look at some of the routing policies that are used for BGP, then security, look at the scaling. We'll see some real-world applications of BGP and then delve into some of the challenges and future of BGP, and then finalize with a conclusion and our references. Moving on, a quick introduction of what BGP is. So the BGP operates as an exterior gateway protocol in the computer networking world, and unlike typical interior gateway protocols like OSPF, ISIS, and ERGRP, which tend to manage routing within an autonomous system, BGP handles routing between different autonomous systems. And as you can see here, you can see each of these entities represent an autonomous system. We have autonomous system 100, 300, 200, and 400. BGP also facilitates the exchange of routing and reachability information among autonomous systems, and it does that to enable autonomous systems communicate with each other, which allows them to make informed routing decisions based on certain factors like network policies, traffic load, and cost. And then BGP's decisions are heavily reliant on path, network policies, and rule sets. Okay, moving on, let's see BGP basics. Here we'll be looking at what an autonomous system is, and then BGP peering relationship, as well as BGP route advertisements. So basically, AS autonomous systems are networks or collection of networks managed by a single entity, such as an internet service provider or, say, a large enterprise. And quickly explain what this means using this diagram here. So we can see that the whole of this is an AS. The whole of this is also an AS, and the same goes for this. Right, so each of these are ASs and individual entities by themselves. Now we have AS 1, 2, and then we say maybe 3 for this. Now the next thing is BGP. BGP has basically two types of peer relationship. We have the external BGP, which is the eBGP, and then we have the internal BGP, which is the iBGP. For the eBGP, this relationship exists between BGP routers in different autonomous systems, and it's basically between the routers on the edge. So for this AS, this is the router on the edge. For this one, this is the router on the edge, and this one, this is the router on the edge. And these are where the eBGP connections happen. So eBGP, for a recap, is between routers in different autonomous systems. iBGP operates within a single autonomous system. So within this autonomous system, you have an iBGP, and there you have communication between routers that exist within the same autonomous system. Now going to BGP route advertisement. BGP advertises routes to its neighboring neighbors, like this to this and this, which are on the edge. And when a router learns a new route, it can propagate this information to its neighboring routers through what is called BGP updates. And it allows for flexible route advertisement strategies as well. We'll see what all of those entails as we move on. So next we have the BGP path selection. BGP routers evaluate multiple paths to the same destination, considering pretty much various attributes to determine what the ultimate route will be. And unlike our interior gateway protocols that prioritize paths based on simple metrics like hop count, which ERGRP uses, or cost, which OSPF uses, BGP employs a more complex path selection process, and we will explore what these processes are. So first, we'll begin with the weight. Now, the weight is a Cisco-specific parameter influencing path preference within the same router. So it has to be within the same router. And the path width, the higher weight is always preferred. Local preference is set within an autonomous system, and it determines the preference for a path. So it's used for outgoing traffic to determine which path to use, right? And for this, the higher local preference is always preferred as well. Then you have the originate, which is basically where the routes are being originated from. And the routes that are originated locally from that specific router, let's say this router, for example, the routes that are originated from this router will be more preferred over those that are inherited into the router from other autonomous systems. Then we have the AS path length. AS path length is just basically the hop count of the advertised route, how many hops it has passed through, how many autonomous systems it has passed through. So if it has passed through up to 7 autonomous systems, the one that has passed through a lesser number, say 3, 4, will be more preferred. So for AS path, shorter lengths are preferred. Then we have the MED. The MED is acronym for multi-exit discriminator, and is used for path selection when multiple paths exist between different autonomous systems. Lower is always preferred here. And of course, I already explained what EGP and IBGP mean. And EBGP is always preferred over IBGP. And if none of these requirements are satisfied, right, what then happens is the neighbor router address is used. Okay. So moving on to BGP routing policies, we basically have 3 primary things. One is inbound and outbound traffic engineering. Then you have route filtering, and then BGP communities. I'll briefly explain what all of this means. So inbound and outbound traffic engineering is just determining how your routes come in and how they go out, right? So say for R3, you want to send a packet all the way to R5. And let's assume that this is a shorter path, right? This is a shorter path. However, you want the route to always prefer this one. So you want it to always prefer R3 to R4, then to R1 before getting to R5, rather than use the shorter. In a typical real world scenario, the shorter path is always the preferred one for you to use. And in fact, let's even say you want it to prefer the shorter path to the longer path so that your packets are delivering much faster, right? Then that is where you do what is called the inbound and outbound traffic engineering. Route filtering, basically BGP filters routes based on defined criteria like the prefix length and AS paths, and enhances security policy enforcement. For BGP communities, these are just like a group of routes based on shared characteristics, and you can enable actions like route preference and traffic engineering when using your BGP communities. Next, we quickly look at BGP security, BGP hijacking, BGP route leaks, and BGP sec. So BGP hijacking occurs when illegitimate routing announcement divert traffic to unauthorized destinations, and this can result to traffic interception or denial of service, posing significant security risks to the network. BGP route leaks happen when a router in one autonomous system advertises a route learned from another AS to a third AS. And then all of this can be easily mitigated using BGPsec. BGPsec is short for BGP security. And what this does is it uses a cryptographic verification of routing information. It ensures the integrity and authenticity of BGP updates, mitigating risks associated with BGP hijacking as well as BGP route. So primarily BGP sec aims to improve the trustworthiness as well as the resilience of the global internet routing structure. Next, we'll look at BGP scaling, which addresses the challenges of managing large networks efficiently. We have primarily three concepts: BGP route flap damping, BGP route reflectors, as well as BGP confederations. Now, the route flap damping is a mechanism used to mitigate instability caused by frequent changes in BGP route advertisement, and it helps reduce the impact of route fluctuations on the stability of the global routing system by penalizing routes that flap excessively. So you have routes that come up, advertise a particular network or prefix, and then go down, and then continuously do this for, say, a certain period of time. What the route flap damping does is it suppresses it and then prefers another route. The route reflector, just like you have here in the middle, is just more like a connection between other BGP routers or BGP speakers, and they are primarily used in large-scale BGP deployments to reduce the complexity of full mesh BGP pairings. They allow for hierarchical route propagation within autonomous systems so that it reduces the noise, so that any routing that needs to be done, the route reflector can do it and send it to the BGP speakers. So on the physical data part, this route reflector is connected to all the BGP speakers, and for, say, router A to communicate to router P, it will need to go to the route reflector first before the communication goes there. However, this is just a physical or data connection, right? Logically, these two communicate directly. On the control plane, they communicate directly. I mean, if you don't know what control plane means, that's fine. So we have the control plane, we have the data plane, but that has to do with routing. Finally, for confederations, these provide another method for scaling, and almost like what I explained earlier for the BGP communities, this approach helps manage BGP scalability and reduces the need for full mesh internal BGP pairings. Real world applications of BGP: internet service provider. ISPs provide businesses and individuals with access to the internet. You have content delivery networks, which are basically used for pushing content as close as possible to the users. BGP is the major factor why this happens. And then one of the most popular ones is your multi-homed enterprises, where you can have like 2 instances of connections to an ISP connecting to, say, maybe your HQ. Let's say your HQ is here. So you are multi-homing it so that you can connect multiple ISPs, and here you can determine how traffic inflow and outflow is determined using the traffic engineering concept I explained earlier. You can also see our route reflectors here as well, acting in both clusters, and of course you can see the concept of our eBGP. So this will be an eBGP. Any routers that exist within here will be iBGP. Same iBGP here as well. All right, so yeah, let's explore the evolving landscape of BGP, encompassing both existing hurdles and potential solutions. For scalability, BGP struggles to handle the rapid growth of the internet, especially in large networks like ISPs and cloud providers. Particularly the rise of concepts like IoT, mobile devices, and cloud computing exacerbates these challenges, and solutions may involve protocol optimizations and technologies like route summarizations. We also have security concerns for BGP. BGP is like the routing protocol of the internet, and addressing these threats require robust authentication mechanisms like RPKI and BGPsec. We also have the prefix filtering that also help mitigate these risks, and then potential solutions like I mentioned before. RPKI, it provides cryptographic verification for BGP route announcements, and it ensures that the legitimacy of IP address ownership, and it prevents route hijacking as well. Other solutions, like I said previously, BGPsec, you can use BGPsec and any other route validation mechanism. To conclude, throughout this presentation, we've delved into the intricate world of border gateway protocol. We've covered its vital role in the internet infrastructure. We discussed the challenges facing BGP, including scalability issues as the internet expands exponentially, security concerns such as hijacking and route leaks, and potential solutions like RPKI to enhance security reliability. Additionally, we explored how BGP's scalability struggles and security vulnerabilities pose significant risks to the stability and integrity of the internet routing infrastructure. And looking to the future, advancement in technologies like the RPKI and BGP, these are actually very promising, and they are offering good backbone to how BGP works. And then finally, as we navigate the ever-evolving landscape of the internet, addressing the challenges and fortifying the security of BGP will be crucial for sustaining the internet's role as a fundamental tool for connectivity, innovation, and perhaps economic growth. And here I have the references that were used for all of the information regarding the BGP concepts. If you need more information, please feel free to look up any of these for a more intense and extended study. If you have any questions, please feel free to reach out to me. First, primarily through the link that will be posted on Canvas, and then either through my email or my phone, and I'll be more than willing to help. I hope this session has been informative for you, and I'd like to thank you for viewing.